Model number 4. So model number 4 is nothing but a free damp single degree of freedom vibrating system. So already I have explained what is free damp, what is single degree of freedom vibrating system. Okay. So basically in your model number 3, what we have studied free undamped. Okay. We have studied free undamped. Okay. Now in this case, there is a damp. Now what is the difference exactly between the free undamped and free damp? That we know. Okay. So basically, as far as the last model was concerned, so what was an example? We have considered spring mass simple system and we have considered X. Okay. So initial displacement X was given to the mass n, right? Initial displacement X was given to the mass n, and then there was the vibration inside the system, and then what we did, we find out the natural frequency omega Fn. Okay, we find out the natural frequency Fn, right? So we have used D-Alembert principle, we have used energy method. Okay, so lot of methods we have used, 2 to 3 types of methods we have used, and we have started find out the natural frequency. Okay, so here there was no external damping. There was no external damping, right? Means what? We haven't provided, so only there were two elements, M and K. Okay, there were only two elements or two parameters, M and K. There was no third parameter C, which indicates the external damper. Okay, now in this module, that is a module number 4, you have to introduce this third module, that is a C. So now the system will become MCK. Okay, and if you look at the figure, this will be the figure, right? So here you can see that now there is a parameter spring, parameter mass, and damper C. Okay, and this is nothing but the X. Now again you try to understand that this is free damp. This is free damp. What do you mean by the free damp? Again, we are not applying the continuous force F. F is equal to, let us say, A sine omega t or something like harmonic excitation. We are not providing this continuous force. Here also I am giving a only initial displacement. That is why it is called as a free vibration, and only here we are providing an external damper, so it is called as a free damp. So that is between the free damp and free undamp. Already I have explained. Okay. So basically now this system becomes MCK. Okay. Now what was the anybody? What was the equation of motion for module number 3, free undamp? What was the equation of motion we were getting? We were getting equation of motion mx double dot plus kx is equal to 0. Mx double dot is nothing but the inertia force which was governed by which governs the mass. Kx is nothing but a spring force governs the spring. Okay. Now we will have a third element, that is a damper, and so we will have that equation Cx dot. So equation of motion becomes mx double dot plus Cx dot plus kx is equal to 0. Again here 0, why? Because we are giving only a initial displacement. We are not applying a continuous force F. Okay. Now your aim is to find out this equation, derive this equation mx double dot plus Cx dot plus kx dot, and find out a natural frequency omega n or Fn. And then what are the different types of damping? Now, before we start with the actual mathematical analysis, let us understand what is damping. Okay. Now, what do you mean by the free undamp? Free damp. Okay. External resistance or a damper C is provided in the vibrating system. So whenever the external resistance or damper C is provided in the vibrating system, it is called as a free damp vibrations. Okay. So this is the first point you should understand. Second point is what? Damping is the resistance offered by a body to the motion of the vibrating system. So damping is nothing but the resistance to the motion. Damping is nothing but the resistance to the motion. Now obviously this resistance to the motion can be internally, it can be externally. So here we are providing an external damper, or you can call it as an artificial damper, a damper which is designed by you or designed by an engineer, and that external damper or artificial damper provides the resistance to the motion, and it is called as a damping. Okay, and damping is denoted by the damping constant C. What is C? C is nothing but a damping constant. What is the unit? We'll understand. Okay. So damping is denoted by damping factor zeta. So this is the factor zeta. This is called as zeta. Okay. So how do you denote the damping mathematically? So mathematically, damping is denoted by the factor zeta. So this zeta is very important as far as this damping is concerned. Okay. So now guys, try to understand that we are incorporating new terms, new parameters. So what are the two parameters till now? One is C and second one is zeta. So these are the two parameters what we have already studied, what we have introduced. Initially we have introduced M, then we have seen K, then we have seen omega n or Fn. Okay. So these are the four, or you can say the parameters what we have studied. and we know that omega n is equal to square root of k by m in radian per second. So this we know. So now I have introduced two parameters. Okay. So basically, what does this damper do? You know that the kinetic energy stored inside the mass, which is given by 1 of mx dot square, and inside the spring, strain energy is stored. What is that strain energy? 1 of kx square. Okay. So this is what we have already defined. We have used in solving the problem. Now, what is this damper? Function of damper. The function of now this kinetic energy is converted to the potential and potential to the kinetic vice versa in the mass and the spring. So this is happening in case of the free undamped. But in this case, what is happening? This damper dissipates the energy. So what is the function of damper? The basic function of damper is to dissipate the energy of vibrating system and reduce the amplitude of vibration. This is very, very important. Now guys, I have already explained you the diagram of time response analysis. What is that? If you draw a diagram of t versus let us say x is the displacement, you can see that initially the amplitudes are high and the amplitudes are go on decreasing. Okay. So this, if I take this as a mean line or the desired line, this is nothing but the x1, this is nothing but the x2, this is nothing but the x3, x4 and xn, so on. Okay. So these x1, x2, x3 are nothing but a decreasing amplitude. So you can see that this damper, which dissipates the energy of a vibrating system, will reduce this reduce this amplitude. Means what? The system will come to the steady state. Now, already I have explained the concept of transient and steady state. So system comes to the steady state, transient system vanishes out. Means what? The system remains for a less time in the transient zone. Transient zone means what? This zone where the output is changing with respect to time. So basically, these amplitudes of vibration are reduced, and then the system reaches to the steady state. Okay. At the start of the vibratory motion, amplitude of vibration is maximum, which decreases with time. So as I shown in the graph, you can I have already shown in the graph. Na? Initially the amplitudes are maximum and they will go on decreasing, and finally they may come to the steady state. Okay. So let us say this is x1, which is maximum, and let us say this is xn, which is very, very minimum. Okay. So initially, this why happens exactly? Why this happens exactly? Because initially, when there is a convergence of energy and when the vibration occurs in the system, initially the damper is not into action. Damper comes slowly into the action, and as the damper slowly comes into the action, this amplitudes will go on decreasing. That is why at the start of the vibrating motion, the amplitude of vibration is maximum, which decreases with respect to time. So this is all about the theoretical part. I hope you have understand this. Okay. Now guys, you can see this. Okay. You can see this diagram. Let us say this is x. Now I have already shown you. I can divide this diagram into the two parts as I showed. So what is this first part? This first part is called the CT of t, and the second part is called as the CSS of t. What is this CT of t? Transient state. This CT of t is nothing but a transient state or transient phase. This CSS of state is nothing but a steady state phase. Steady state phase. Okay. Now basically, what is transient phase? What happens in this transient phase? In this transient phase, you can see that initially the output amplitude was maximum and the amplitude goes on decreasing, and finally the steady state, the system reaches to the steady state. Means what? There is no any change in the output with respect to time, or there is a very, very minute change in the output with respect to time, or the output remains constant with respect to time in this zone. So this steady state zone can have like three types. One is what? It can be a straight line. It can be a constant line. Constant line means what? The output remains constant with respect to time, or you can say the output is varying at very, very small amplitudes. Okay. So that is all about a steady state. So every system passes to the transient state and reaches the steady state. Now basically, one point I have explained that this time, this particular time is called the settling time. This particular time is called as the settling time. What is the settling time? The time taken by the system to reach the steady state, to reach this point, to reach this phase, CSS of phase called the settling time. Okay. So settling time should be as minimum as possible, and the settling time depends upon this damping, Zeta. Okay. So what is the type of the damping? So there are normally 3 to 4 types of damping which you'll be studying in your particular syllabus. So depending upon the types of damping and the amount of damping, so very, very important, type and amount of damping. So there is one statement which I will show, very, very important. The rate of decay of amplitude depends upon the type and the amount of damping. What is rate of decay of amplitude? If I draw this graph, you can see the rate of decay is exponential. Rate of decay is exponential. E raised to something, e raised to something means what? These amplitudes x1, x2, and x3 are decreasing in an exponential form. If I draw this, I will show you again. You can see these amplitudes are decreasing in an exponential form. Okay. So this rate of decay of amplitude, this amplitude will decrease, the amplitudes, that is x1, x2, x3, will decay or will vanish at a faster rate or at a slower rate, or they will not vanish. Maybe they can go to the infinity, or maybe they can go to the infinity. Okay. So whether this amplitude reaches the infinity or this amplitude goes to the zero, okay, everything depends upon this type and the amount of damping. So as an engineer, depending upon the application, depending upon the conditions, by doing the mathematical analysis, you have to incorporate this damping. So basically in mechanical vibrations, and basically for this particular model, the study of graphs are very, very important. Okay. So as I said that model number 3 and model number 4, time domain graph. Time domain graph means what? Time response graph is very, very important. And model number 5, we will study the F domain graph. F domain is what? Frequency domain graph. Means what? On n axis, instead of time, you will have a frequency. Okay. So that is the latter part. I will explain you later on. Okay. So basically the main aim of providing a damping in the mechanical system is to control the amplitude of vibrations to avoid resonance. Now guys, you know that resonance is nothing but when omega is equal to omega, the amplitude of vibrations, you can see that this amplitude of vibrations will go on to the infinity. Means what? You have to control the amplitude of vibration. Means what? They should not reach infinity. They should reach to the zero. May not be it is completely equal to zero, but it should approach to the zero, or maybe it remains constant at some time, after some time. Okay. So you have to control the amplitude of vibrations to avoid the resonance, because if amplitude of vibrations, if x1 and xn, you find that x1, xn, let us say, reaches to the infinity, the system will fail. Okay. So that is why you have to provide this damping. So before providing a damping, is it not like you cannot provide damping as of you decide? Okay. It is very, very important that there is some range. You have to do it some mathematical analysis or maybe some software analysis, right? Okay. Now basically, now guys, I am up to the module number 4, that is a free damp. Okay. Now basically when you study this free damp condition, there are two important parameters. What is the first parameter? The frequency of damp vibration, omega d. Now what is omega n? Omega n is nothing but a natural frequency, or you can call it as a natural frequency. You can call it as a natural frequency of free vibration. Natural frequency of free vibrations, or you can call it as the frequency of a free vibrations is called as a natural frequency. Okay, and this omega d is nothing but the natural frequency of damp vibration. Natural frequency of damp vibration. It is also natural frequency, but it is called as a natural frequency of damp vibrations or frequency of damp vibrations. Now, basically, guys, in last module, you haven't applied any damping. You haven't applied any C. Okay. So now, in this case, in this particular module, you are providing some zeta, that is a damping. Okay. So corresponding frequency means, for example, let us say that the initially frequency is omega n. Why initially frequency is omega n? Because initially this damper C or zeta is not into the action. So initial frequency, in this case, we are considering is omega n, but as this C comes into the action, you can see that these oscillations are damped. These oscillations are damped, and these damped oscillations can be, sorry, the frequency corresponding to this damped oscillation is called as omega d. So frequency corresponding to this damped oscillation is called as omega d, and initial frequency we consider as omega n. And at some point, okay, at some point your omega d will become zero. Maybe after some time your omega d becomes zero. So when omega d becomes zero, so initially it is omega n, then it is omega d, and after some time it becomes omega d may become zero. And if this omega d becomes zero, what is that case called as? That I will explain you in the next slide. Okay. So now guys, I hope you have understand this. And second parameter is rate of decay of amplitude. This rate of decay of amplitude is nothing but a logarithmic decrement. This is very, very important term, guys. See, you can see that how this is decaying exponentially. Okay. So the rate of decay of amplitude means what? The amplitudes are decaying from x1 to x2 to xn. So at what rate it is decaying? Okay, so that rate of decay of amplitude is called as a logarithmic decrement, and mathematically it is denoted by del. So del is nothing but a logarithmic decrement, which is a mathematical parameter which gives you the idea about rate of decay of amplitude. I hope it is clear to all of you. Okay, so rate of decay of amplitude is called as a logarithmic decrement, or it is a parameter which is nothing but the which indicates the rate of decay of amplitude. Okay, so guys, I hope you have understand these are the two very important parameters which I have explained you in today's theoretical part. What are the two parameters? One is omega d and another one is omega n. Sorry, one is omega d and another one is del. Okay, so now we move on to the next part within a shorter period of time. Okay, so please message me. Have you understand this all the theoretical parts which I have explained? What is log? See, we also have to derive an expression for the logarithmic decrement. Okay, so don't worry about that. So that we will derive in meantime. Okay, so now just message me whether you have understand or not all these things. Hello. Yes, message me yes or not. Before I go to the mathematical analysis, tell me whether you have understand this theoretical part. Okay. Any doubt in this, you can ask me. Okay, because unless and until you understand this theoretical part, I cannot move on to the next. Okay. Sure. Now, we'll move on to the next part. Okay. Now viscous damping. Now basically you have understand what is omega d, what is logarithmic decrement. Okay. Now next part is to derive. Now you know what is omega n. What is omega n? Square root of k upon n. Okay. Now you have to derive the equation for the omega d. You have to derive the equation for the del. Okay. Mathematically. Now first of all, types of damping. Now basically there are two types of damping. First is the viscous damping and second is the Coulomb's damping. Okay. Coulomb's damping is also called as a frictional damping. Okay. You can see the friction between the two dry mating surfaces. Okay, let us say this is a surface, and on the surface this is a mass. Okay, and you are applying a mass, force to the mass. There is a motion to the mass. So this motion, there is a relative motion between this mass and let us say the surface. Okay, or I can say the motion between the mass and the surface. So corresponding, you can say the force which is opposing this motion is nothing but a frictional force. That is called the Coulomb damping. And the first one is the viscous damping. Okay, so in this particular model, we will be deriving, we'll be studying two types of damping. One is the viscous damping, and second is the okay. So you can take an example of this damper, or you can take an example of this damper, which is used in automobiles, and that is nothing but the suspension system of an automobile. Okay, so damper which we use in the suspension system of automobile is the basic example of a viscous damping. I hope it is clear to all of you. Okay. Now, basically, what is viscous damping? Let us first of all understand. When the system vibrates in a fluid medium like air, gas, water, or oil, then it is offered resistance by the fluid to the vibrating body, which causes energy. So, what is the function of C? To dissipate the energy. Function of C is to dissipate the energy. Which energy? There is a kinetic and potential energy. So, because of that energy, you have to the system is vibrating and you have to dissipate this energy. Now to remove this energy, if you are using air, gas, water, or oil medium, means what? The resistance is offered by this air, gas, water, or oil. Then such type of, you can say, damping, such type of resistance to motion is called as a viscous damping. Such type of motion is called as a resistance to the such type of resistance to the motion is called as a viscous damping. I hope it is clear to you. Okay, so such a damping is called the viscous damping. I can give you small. You can say I will explain the small principle of the viscous damping. Okay, let us say that this is a small you can say cylinder. Okay, so inside the cylinder, let us say there is a fluid. Okay, so let us say there is a fluid inside the cylinder. Okay, now if there is a fluid inside the cylinder, what we'll do? We'll put some piston. Let us say this is a piston. Okay. Now let us say this is a piston. Okay. Now, what is this? This is a piston, and what is this? This is a fluid. Okay. So same principle is used in the automobile suspension damper. Okay. Now, this fluid is basically called as a viscous fluid. This fluid is called the viscous because it is designed or it is the fluid we are using is having some specific viscosity, right? So that is why it is called the viscous fluid. And now basically what you do, let us say you apply the force on the piston. Okay. Now when you apply the force on the piston, this piston will try to move in a downward direction against this fluid force. So what is this fluid force which is acting upward? Let us say this is a fluid force. Okay, this is a fluid force act which is acting upward to this downward motion of the piston. So this resistance to the motion is provided by this fluid to the motion of the piston. So then whatever the energy is created because of the application of the force, so that energy will get dissipated because of the resistance provided by this fluid. Okay, and this is the principle of a viscous damping. So same principle we are using in this particular automobile suspension system. Okay, now I will not explain you the working principle of this because this you will understand in the last step, that is automobile engine subject. Okay, so just to give the example, I have explained here. Okay, so here also you can see the construction, or you can watch any YouTube video also. You will get the construction of this, how car suspension system works. Okay, so I have just explained the example here, right? So such a damping is called the viscous damping. So basically, viscous damping. Now see, what is the aim? You have to mathematically model this viscous damping. You have to design this viscous damping. So obviously, you should know on what are the parameters on this viscous damping depends upon. The first is the relative velocity between the two vibrating surfaces of a body. Two vibrating surfaces of a body means what? They're separated by a viscous fluid film. Two vibrating surfaces or a body which are separated by the viscous fluid film. So what is the relative velocity between them? That is the first parameter. Viscosity of fluid and the dimensions of the damper and the fluid. Okay, so these are the two parameters on which this viscous damping depends upon. Okay, now the fluid film which resists the motion is called the damping force F. So what is this damping force F? F is nothing but a damping force. Okay, F is nothing but a damping force which is given by Cx dot. F is equal to, because in the first maybe second or third lecture I have explained that the damping force F is directly proportional to the velocity x dot. So F is equal to Cx dot. C is the damping constant, and this F is equal to Cx dot is nothing but a damping force. Okay, so in case of the viscous damping, forget about the Coulomb damping or frictional damping. In case of the viscous damping, this fluid film which resists the motion, or you can say the resistance to the motion offered by this fluid film is called as the damping force, and this damping force F, is opposite to the motion x. Means what? If you are providing a motion x in a downward direction, this F damping force will be acting opposite. You try to understand that inertia force, spring force. See, we have a guys three force: mx double dot inertia force, kx spring force, and cx dot damping force. All this will oppose this F. F means what? Applied force. Okay, or you can say they will oppose this x, applied motion. I hope the fundamental of the viscous damping is clear. Okay, so now let me consider some diagram. So let us say this is a damping. Now let us say you are applying F is the applied force. So you know that the x, that is the displacement of the mass m, will be in the direction of the applied force. So what is this C? C is nothing but a damper. So this F is nothing but a frictional force, or you can call it as a F. You can call it as a damping force. F is called as a damping force. This damping force F is equal to Cx dot. This damping force will oppose this x or oppose this F. Means what? This damping force is trying to bring this mass, or you can say trying to bring this system to its equilibrium position. Is it clear, guys? So basically this diagram I have already explained you. So F is directly proportional to the x dot. F is equal to Cx dot. So F is equal to damping force Newton and damping coefficient Newton seconds per meter, because C is equal to F upon x dot, that is equal to Newton upon meter per second. So Newton seconds per meter. Okay. So this I have already explained you in the last lecture also. Okay. So is it clear the fundamental? Now let's move on to the part of derivation part. So first of all, write down the heading: damp free vibrations with viscous damping. So first I will derive the equation of motions for the damp free vibration with viscous damping, and secondly I will derive for the Coulomb damping. So what is viscous damping? The resistance to the motion is offered by the fluid medium when the particular body or a vibrating system is vibrating inside the fluid medium. Best example is an automobile suspension system shock absorber or a damper. Okay, there you have a piston and cylinder arrangement, and you are providing a viscous. So basically, what is in your hand? Viscosity of the fluid, dimensions of the damper, and the relative velocity between the two surfaces. So these are the parameters on which the viscous damping depends upon. Okay, there is law called as the Newton's law of viscosity, mu. There is a law called as the Newton's law of viscosity, which you have studied. Newton's law of viscosity. Okay, so this Newton's law of viscosity governs this viscous damping, which you have already studied in the fluid mechanics. Okay, so I will not go into the detail into that. Okay, so I hope everybody knows this Newton's law of viscosity. Clear? Okay, so consider the spring mass system. Now, guys, in the last problem, we haven't considered this C. So now we will be considering Baki. Rest is same. Rest is same. So consider the spring mass system, and let us say that X is the small initial displacement. X is the small initial displacement given to the mass m. So once you give a small initial displacement to the mass m, X will be the motion of the spring, and again there will be x dot in the velocity. X dot will be the velocity induced inside this C, and x will be the displacement inside here. Okay, and acceleration will be induced inside the mass, right? So whenever you are applying a small displacement x to the mass, acceleration will be induced in the mass, x displacement will be induced in the spring, and velocity will be induced inside the damper, all in the direction of the applied motion, that is the x. Okay, so guys, what is the first step? The first step is to draw the free body diagram of a mass m. So let me draw a free body diagram of a mass m. Let me draw a free body diagram of a mass m. So what is the free body diagram of a mass m? Let us say m. So let us say x is the displaced motion x given in the downward direction. Now tell me, what are the anybody? What will be the forces acting, and what will be the direction of the forces acting on the mass m? What are the forces acting on the mass m? I want to answer from your side because we have already studied this. Yes. Which is the first force which will act on the mass? And direction. Yes, anybody? Now, here the damper has been induced on incorporated. So, which is, tell me. Hello? What are the forces acting on the masses when you are giving a small displacement x? Which is the first force? Anybody? Hello? Are you understanding my question? Yes. What is the first force? Or any force, you know. Am I audible? What are the forces acting on the masses? Hello? Hello? Am I audible?
mx double.
Yeah. So first force is mx double dot. What is mx double dot? Inertia force. Inertia force always acts opposite to the displacement x. Second is what? Spring force k into x, opposite to the displacement. And what is third force? Cx dot. What is Cx dot? What is Cx dot? Damping force. So inertia force, spring force, and damping force, these are acting on the mass for this particular system which I have taken and opposite to the displacement. Okay. Now what is the next step? Apply D'Alembert's principle. Apply D'Alembert's principle. Now when you apply the D'Alembert's principle, what is D'Alembert's principle? Summation of inertia force plus external force is equal to 0. So what is inertia force here? Summation of mx double dot. And now what are the external force? In last problem, we have kx, that is spring force, as external force. Now we have external force cx dot. Okay, so that is equal to 0. So let me call this as equation 1. So this is the equation of motion for a system which is vibrating with damp free vibration with a viscous damping. So what is the equation of motion I've got? Mx double dot plus kx to cx dot. So this is the equation of motion which I have got, and now we have to resolve this equation of motion. Okay. Chalo. So according to the D'Alembert's principle, I have got this equation. So what is the equation? Summation of inertia force plus external force is equal to 0. Mx double dot plus cx dot plus kx is equal to 0. Equation 1. Okay. Now this equation number 1 is, now this mx double dot means what? M into d square x by dt square, right? Plus c into dx by dt plus k into x is equal to 0. Now if you look at this equation, what is this equation? This equation is called the linear differential equation of second order. Why? Because you can say the highest power is 2, so that is why it is called the second order, and it is a linear differential equation of a second order. And its solution can be written as, anybody can tell me? Now already in the mathematics we have studied. What is the solution as per the mathematics or as per the math for this linear differential equation of second order? Okay. What is the solution? Okay, I will give. The solution is x is equal to e raised to st. x is equal to e raised to st is the solution of this linear differential equation. What is this linear differential equation? Mx double dot plus cx dot plus kx dot. Okay. Now if x is equal to e raised to st, so basically if you differentiate this, let us say you are taking dx by dt is equal to x dot, what will be happen? S is equal to e raised to st. If you are taking dx square by dt square, that is equal to x double dot, it will become s square into e raised to st. Okay, so this is the differentiation. So I have got these three terms, 1, 2 and 3. Okay, so this is not, see, this is not a complete solution. It's not a complete solution. Complete solution I have to find out at the end. I will get a complete solution, but this is the initial solution, you can call. Just by by considering this as a linear differential equation, I am getting this solution. Okay, so finally you have to find out the complete solution. Okay, why you have to find out the complete solution, that also I will explain you as the mathematical procedure proceeds. Okay, now what is e? E is the natural logarithm base, s is the constant, and t is nothing but the time. So this already you know. Okay, next. Now basically you have to put this in equation number one. Put all this. Put x, x dot and x double dot in this equation number one. X, x dot and x double dot, you put this all in the equation number one. Okay. So what you are getting? Mx, see what is the guy's basic equation? Mx double dot plus, see why I am doing this now, at the end I will explain you, because if I explain you why I am doing this, you will not understand. Till now you have understood it. I have taken a simple spin mass system because my condition is free damp, viscous damping. Okay. So from that I have got equation of motion. It's a linear differential equation of second order. I have got the solution. I have put it in the equation. Equation of cx dot plus kx is equal to 0. What is x double dot? S square into est. Okay. So from this you can, this est, 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 e raised to st will get cancelled, and finally you are getting this equation. So guys, what is the equation? Ms square plus cs plus k. So guys, if you try to understand that derivative, this derivative I have converted into the s form. That is a very simple form, because initially it was into the time domain. It was into the time domain, that is dx d square x by dt square. Now this time domain I have converted into the s form. Right? Means what? I have simplified this linear second order equation, because unless and until you simplify, you will not get a complete solution. Okay. So now above equation is called the characteristic equation of a free damped vibrating system. Above equation, which equation is called the characteristic equation? This characteristic equation you can also call it as a frequency equation. Frequency equation means what? Now you can see what is the order of this? What is the order of this? Highest order 2. So if the highest order is 2, means it is a second order equation. Means what? It will have a two roots. It will have a two roots. Two roots means what? S1 and S2. So now your aim is to find out this S1 and S2. This is called the characteristic equation. Why it is called as the characteristic equation? Because you are equating it to the zero, and when you are equating this linear differential equation to the zero, you are getting a two roots, that is S1 and S2, and that is why it is called the characteristic equation. And these two roots which you are getting are nothing but the frequencies. Means what? You are getting frequency omega 1n and omega 1n2. Okay, means what? You are getting two frequencies, omega n1 and omega n2. हे जे two roots तुम्हाला मिळत आहेत, they are nothing but frequencies, because finally ultimately we are finding the frequencies. So two roots are nothing but the two frequencies which we are getting, and that is why this characteristic equation is also called as the frequency equation. So now let us find the frequency equation. So guys, what is the formula to find out the roots of the linear second order equation? Anybody? What is that formula? That formula is S1. Now I am getting a two roots, S1 and S2. Okay, so what is the formula? Minus b plus minus square root of b square minus 4ac plus 2a. So what is minus b? Minus b means what? C. What is bc? What is a? M. And what is c? It is k. Right? So this is a, this is b, and this is e. So I am getting s1 to is minus c plus minus square root of c square minus 4nt upon 2m. So s1 and s2 means what? S1 and s2. These are the two roots. Why two roots? Because this is a second order equation, linear second order equation, and it is when I am equating it to the zero, so it is called a characteristic equation or a frequency equation. I am getting a two roots. Okay. So what are the two roots I am getting? I am getting minus c upon 2m plus square root of c upon 2m square minus k upon n, and minus. Okay. So minus c upon 2m plus so and so is the first root, and minus c upon 2m and minus so and so is the second root. Okay. Now guys, in the module number 3, the mathematical analysis was slightly easier. Now the mathematical analysis has become complex because the C has been introduced, the third term C has been introduced. Again in model number 5, the mathematical analysis will become slightly complex because again there will be F. Here now F is 0. Okay. So guys, tell me, have you understand how I have find out two roots S1 and S2? Message me so I can move forward. Okay. Have you understand how I got the two roots? Okay. So this root number 1 S1 and root number 2. Okay. So these are the two roots of an equation for this particular spring mass system having mck as a parameter. Is it okay? Okay. Now here the two solutions of differential equation of equation 1. So what are the two? So what is the equation? Basically x is equal to a raised to initial solution. So now I have two roots, so I will get e raised to s1 of t and e raised to s2 of t. Okay. So this is the first solution. This is the second solution. Okay. Why I have got a two solution? Because I have a two roots. Okay. Now general solution. So what is general solution? So finally, I have got two solutions, solution number 1, solution number 2, because I have got two roots, S1 and S2. So now finally, I will get a general solution or a complete solution. So general solution is x is equal to a into e raised to S1 of t plus b into e raised to S1 of t. Okay. So guys, try to understand that. Here, I know what is S1, I know what is S2. So general solution x, what is x? X is nothing but a displacement, or you can call it as an output. See, if I draw a diagram of t versus x, so this x is nothing but the output, that is c of t. This x is nothing but a displacement, that is output. It is with respect to time, so I am taking it as a c of t. So it is x is nothing but a displacement. So this x is equal to a into e raised to s1 of t plus b into s1. But now your final solution is not over. Why? Because a and b are nothing but the arbitrary constants. Now your aim is to find out a, and now your aim is to find out b. Okay. So guys, anybody can tell me, you have already solved number of problems in the mathematics. So I have got an initial solution, two initial solutions, general solution, I have got S1, I have got S2. So to get a final complete solution, I have got S1 and S2. Now my aim is to just find out A and B. So guys, anybody have by any chance know how do you have already studied in the mathematics? How do you calculate this? How do you calculate this A and B? By assuming some initial conditions. So what are those initial conditions? So that we will understand, okay, in the next lecture. So let me complete this part. So now basically for further analysis, see, for further analysis of equation 3, which equation 3? Further analysis of this equation 3. Equation 3 means what? X is equal to a into e raised to s1 t plus b into e raised to s2 t. So for further analysis of this equation 3, I have to define some more term. Till now, I have defined term omega d, del, I have defined c. Okay, so these are the three new terms which I have defined. And then I have got this general solution equation. Now some more terms I have to define. What is this c? C is nothing but a damping constant. There is one more term which I have to define, that is called the critical damping coefficient. What is this critical damping coefficient? Let me understand. Okay. Now, this term called as CC. The CC is nothing but a critical damping coefficient. Critical damping coefficient. Guys, these all terms are very, very important. First of all, what is C? C is nothing but the F upon X dot, that is equal to Newton seconds per meter. What is C? Damping coefficient, right? Now, because F is directly proportional to X dot, so F is equal to Cx dot. So critical damping is nothing but some part of is nothing but the C, but it will satisfy certain condition. Means what? If certain condition is satisfied, this C becomes Cc. So now we have to understand when C will become Cc. Means what? When this C damping constant will become a critical damping constant. Let us understand. Okay. So now basically try to understand that if I draw this diagram, sorry, I will use the diagram which already I have. That diagram I will move backward, so it will save my time. Okay. Now this is a diagram which I am using. Okay. Now this is a diagram. Which is the state? Transient state and steady state. Okay. Now the corresponding frequency here is omega d. What is omega d? Frequency of damped vibration. Means what? I have incorporated zeta or c inside the system. That is why the corresponding frequency is called omega d. Okay. Now at some time means what? When this omega d equal to 0 means what? Somewhere this omega d becomes 0. I have already told you that in the last slide that I will explain what happens when this omega d is equal to 0. Okay. When omega d means what, the frequency of damp oscillation becomes 0, this Cc is called as a Cc. I hope you understand this. This Cc becomes a Cc, sorry, this C, critical damping coefficient, sorry, this C, that is a damping constant, is called as a Cc or will become Cc, that is a critical damping constant, where in this graph, this omega d is equal to the 0, right? So guys, try to understand that this C is equal to Cc when the frequency of damp oscillation approaches to the 0 or becomes a 0. And very important point, that motion should be a periodic motion. That motion is a periodic motion. Now in this particular year syllabus, we are considering a periodic motion only. That is a simple harmonic periodic motion. So when the motion is simple harmonic and a periodic motion, omega d becomes 0, where C becomes Cc. There is a critical damping coefficient. I hope you understand this definition. Okay. Now, mathematically we will understand this. We will understand this mathematically. Okay. So critical damping coefficient is the value of damping coefficient at which. Now, what are the two roots? Which two roots are nothing but the S1 and S2. Okay. Now, as I said earlier, guys, what I said that C is equal to Cc when omega d is equal to 0. So mathematically, when this term becomes 0, what is this term? C upon 2m bracket square minus k upon 10. This term becomes 0, right? Means what? When will this omega d is equal to 0? When this term is 0, म्हणजे काय तुमचे S1 आणि S2 हे जे दोन रूट्स आहेत त्यामधली ही जी टर्म आहे, that term becomes 0, then your omega d becomes 0 and C is equal to C, right? So let us do the analysis. Okay, let us do the analysis. Okay, so C upon 2m bracket square minus k upon m is equal to 0, right? So now when omega d is equal to 0, this C becomes Cc. Means what? This term becomes 0, so this C will become Cc. So instead of writing C, I will write it as a Cc. Okay, I know this is slightly complicated, but try to understand what I'm trying to explain. Okay, so now we will solve this. Okay, so from this what I get, Ccc upon 2n bracket square is equal to k upon m, right? I'm getting this. Okay, now from this what you will get, Ccc upon 2n is equal to square root of k upon m, right? Guys, is it clear? Now anybody tell me what is square root of k upon m? What is square root of k upon m? Anybody from your side? What is square root of k upon m? Already derived. What is square root of k upon m?
Omega n.
What is, okay. So guys, I am getting Cc is equal to 2m into omega n. Okay. So this is the one more formula which I have derived for you. Okay. So till now, we know what is C. C is nothing but f upon x dot. We know what is omega n, that is equal to square root of k upon m. Now the critical damping coefficient C is equal to Cc. That is damping constant C becomes critical damping constant when omega d is equal to 0, and you can calculate this from this formula. Cc is equal to 2m omega n. Is it clear? Is it clear or not, guys? Guys, it is clear. Okay. So one more formula you can derive from this. See, one more formula you can derive from this for your sake. See, now this Cc can be written like this: 2m into square root of k upon m, right? If I cross multiply this 2m, I will get Cc equal to 2 upon square root upon m. Okay. Now, if this n, if you put this m inside, it will become km square upon n. So what is this? Cc becomes 2 into square root of k into m. So guys, you have a two formulas for Cc: 2m omega n and Cc is equal to 2 square root of k upon m. Is it okay? Guys, have you understand this? Is it clear? So this is okay. So Cc is equal to square root of 2km and 2m omega n. So Cc depends upon m and k and independent of C. Okay. So basically, what are the parameters on which this Cc depends? It depends upon the omega n. Omega n means what? K upon m means what? K into m. So Cc completely depends upon m and k and is independent of the C. Okay. Is it clear? Okay, and now last point I will explain and I will stop. Now damping factor zeta. Now you know what is damping factor zeta. Damping factor zeta is nothing but a factor which defines the damping constant. Okay. Now what is now guys we module number 3 and module number 4 till now you might have understand or you should understand that they are depending upon they are the time domain. Time domain means what? They depends upon the time, right? Means what? The graph is always called as a time response graph. Okay, so I am always interested in the time response graph. Okay, and you cannot analyze the time response. That is why you are converting it into the S. S means what? It is into the Laplace form. Okay, and this Laplace form can be converted into the frequency domain. That we will understand how to convert this into the frequency domain. Time response is how converted into the Laplace and in the model number 5. Okay, but now you understand that. Here you have a transient state, steady state. Till now, you have understand what is transient and what is steady state. Transient means what? Your output changes with respect to time. And transient means what? Output is constant with respect to time. Okay? Chalo? Okay? So basically, every system, guys, there are some points you should understand. Every system, you can take any physical system, you can take any physical system. Every system takes some finite time. Very, very important. This word is very, very important. Take some finite times to reach means what? It will start from zero and it will reach here. So this is nothing but the finite time. This time period is called the finite time. So every system takes finite time to reach the steady state. Means what? Initially it will pass through the transient. Pass through the transient means what? The output will fluctuate and then slowly this amplitude will go on decreasing and finally it will reach to the steady state. Means what? It will reach this CSS of T phase. So this finite time is called as what? Settling time. This finite time is called the settling time, and the settling time is very, very important, guys. Okay. So basically, in this transient state, there are two conditions. Either this output will oscillate, means what? The behavior of the output will be oscillatory, or behavior of the system will be you can say oscillatory. Transient is the behavior कसं असेल oscillatory, or maybe it can be exponential, like it can be exponential. So here the behavior. So guys, the nature of the system can be only of two types. Either it will be oscillatory and either it will be exponential. And whether it is exponential or whether it is oscillatory, that depends upon this factor zeta. Zeta means what? The value of zeta or magnitude of what is the magnitude of zeta will tell you or will give you either oscillatory or either exponential response. Of whom? Transient state. Means what? In transient state, either system will oscillate or either system will rise exponentially or come to the steady state exponentially. I hope it is clear to you. Okay. Now, the system has tendency to oppose this oscillatory behavior. Means what? Let us say the nature is oscillatory. Let us say the nature is oscillatory. So this system means what? Internal resistance. It is also called the internal. So this system will internally oppose these oscillations. They will oppose these oscillations. Okay, oppose this oscillation. Again, you are also providing the C. So you are providing some artificial damper also. So they will oppose this oscillation and they will try to reduce this finite time. Try to reduce this finite time is what? They will try to reduce this settling time. They will try to reduce this settling, and that is what we want. And that is what we want. So this particular, you can say, the tendency of a system to oppose the oscillatory behavior is called as a damping. This is another damping. What is damping? Resistance to the motion. What is damping based on this graph? The tendency of a system to resist this or to oppose this oscillatory behavior. Okay, I will write here tendency to oppose this oscillatory behavior and try to bring the system to the steady state or reduce the settling time is called as a damping. And this damping is measured by the damping factor zeta. Okay, so in short, moral of the story is that damping factor zeta explain how much dominant the system opposition is. How much dominant system opposition is to the oscillations of a system. Okay, how much dominant system opposition is to the oscillation, it tells us is about this zeta, or this factor zeta explains how much dominant system opposition is to the oscillation of the system. So let us see how do we calculate mathematically. So mathematically, last point, mathematically, damping ratio is defined as zeta is defined as C upon Cc. Now guys, what is Cc? Cc is damping constant. It is nothing but the damping constant. And what is Cc? Critical damping constant. Now guys, I have explained you already what is Cc. Now you have understand why I have calculated first of all Cc, because if you want to find out the zeta, you should know Cc or vice versa. So zeta is nothing but the, what is zeta? Zeta is nothing but the ratio of mathematical. Theoretically, zeta is nothing but the resistance to the motion, or how much the dominant the system opposition is to the oscillatory behavior of the system. Behavior is of only two types, exponential or oscillatory. Okay. So now the ratio of this damping z constant to the critical damping constant is called as zeta. Okay. So finally, you know that zeta is equal to C upon Cc, and what is C? Sorry, Cc 2n omega n. So C is C upon 2n. So sorry, C becomes 2 into zeta into omega n, and C upon 2n becomes zeta into omega n. Now guys, you might have been wondering